All right, I'm Professor Suzanne Boyd. I'm the chair of the Mathematical Sciences Department here at the University of Wisconsin-Milwaukee. And we'll get started with our Marden lecture today, our virtual Marden lecture. And as people are joining, it'll take a few minutes to do introductions anyway. So we'll go ahead and get started. I'm just going to say a couple words about the Marden lecture, and then I'm going to hand it over to someone else to introduce our speaker. So the Marden lecture was actually named after a professor who was in our math department. Now I can't find the tab that I'd opened. So actually, I can put this, I'm going to put this in the chat. I think I can send a chat to everyone. So let's see if that works. So I put a link in the chat because I don't want to say everything at this link, but it's really interesting. There's a bit of a history of our graduate program. And so the Marden lecture series is on honor of Morris Marden. He actually was a professor in the math department, like I said, who founded our graduate program in the 60s. In fact, it made the PhD program in math the very first PhD program at the University of Wisconsin-Milwaukee. And if you look at the link that I sent, it's about the Marden lecture series, but actually I'll back it up a little bit. I think I'll put another link on there. That one has sort of sublinks. There's a biography of Professor Marden, which is really fascinating. And there's his own account about founding our graduate program. There's also some reminiscence there and some other lectures. So I encourage people, in their free time, not in the next hour because you're going to be focusing on the Marden lecture today, but in your free time, I would encourage you to go check that out and read, some of this certainly larger than life biography. Professor Marden, he was born in 1905 and he passed in 1999. He was if you think about sort of what happened in U.S. history in that time period, he lived through some of the most interesting, some really interesting times, I would say. We're in interesting times right now, but he lived through some pretty interesting times. And woven through that was also interaction, I would say interesting historically, but also mathematically, right? Woven through that was his interaction with some pretty significant and famous mathematicians. So I think it's a good read and very interesting. So I would encourage you to read his biography. And then also information about his reminiscences about the graduate program and mathematics. So I did want to ask, is there anyone from the family that wanted to say hello? We could actually temporarily make you a panelist so that you could speak if anyone from the family wanted to introduce themselves. A few minutes. Because this is a Zoom webinar, which we expected a fairly large audience, the participants that you can't speak, you can't turn on your mic, you can't turn on your video, you cannot use the chat either. So for participants, maybe I should have started with this technical issue, right? Participants, if you want to ask questions of the speaker, you need to use the Q&A. So if you move your cursor around a bit, for my computer, it's at the bottom, it appears the chat screen and the Q&A. So someone has already done this. So if you could put questions in the Q&A. Anna Scott. Okay. Jay, would you be able to make Anna Scott a panelist so that she can turn on her video and say hello?
That's actually my daughter, not one of the.
Oh, it's your daughter. I said the family.
Yes, it's my family, not Marden family. So
okay, I'm sorry. I wasn't precise about that. Okay. So Professor Marden had two sons, and one of them settled in the area, and he frequently comes to these lectures. So I don't know if he was able to attend this virtual one. Also, because it's virtual, his other son, who was a mathematician, I believe in Minnesota, might have been able to attend. So what I was saying, if there's someone in the Marden family who's who's on the call who wanted to say anything about their about Professor Marden, invite them. So if you find the Q&A, then you could put something in the Q&A. And so the Q&A is a way that anyone in the audience can send questions to the speaker. He may address them during the talk, but you can send questions there during the talk. And then at the end of the talk, we'll have a Q&A session where our moderator, Professor Hinam, will facilitate asking questions of the speaker. And then tomorrow at 3 p.m., we'll have a math colloquium. So this will be a more, the Marden lecture is a general audience talk. Tomorrow is a more math department talk. So, but that expects to be a smaller audience as it's a bit more technical, but that would be an opportunity for participants to turn on their mic, turn on their video and ask questions in a more interactive format. All right, so maybe it's okay. So maybe that addresses the technical issues and the history of the talk. If anyone has any questions about the mathematics of this talk, or about how to get in touch with Dr. Scott, or about the Marden lecture in general, you put anything that you want to in the Q&A, panelists and the speaker can see that throughout the meeting. All right, so I don't see anybody from the Marden family. So without further ado, hopefully now I've talked long enough for more people to find the link and join the meeting. Professor Deshwan Ji, who is a professor in our department, has been here, I don't know how long, longer than me. He is going to introduce our Marden speaker today, Dr. Scott. So I'm going to say goodbye and turn things over to Deshwan.
Good afternoon, everybody. My name is Deshwan Ji. I'm professor of mathematics. As one of his students, I'm particularly honored to have this opportunity to introduce Dr. L. Ridgway Scott, our Marden lecture speaker. Dr. Scott graduated from the Tulane University with a bachelor degree in 1969. He received his PhD degree from the Massachusetts Institute of Technology in 1973. He joined the University of Michigan in 1978. There, he rose through the ranks from assistant professor to full professor and moved into computer science research as a co-founder of the Advanced Computer Architecture Laboratory, the early center for the study of parallel computing. In 1986, Dr. Scott moved to Penn State University, and in 1989, he moved to University of Houston and became M.D. Anderson Professor in 1995. From 1992 to 1998, he was the director of a National Science Foundation Grand Challenge Research Group at the University of Houston. In 1998, Dr. Scott moved to the University of Chicago as a professor of computer science and of mathematics. He is a Lewis Block Professor since 2001 and a Professor Emeritus since 2018 at the University of Chicago. Dr. Scott has devoted to the research and the teaching of mathematics, computer science, computational chemistry, and mathematical biology for more than 50 years. He had 16 PhD students, I'm one of them, and published about 200 papers. I just checked Google. His Google citation number is more than 24,000. He also published 5 books, including a widely cited book, The Mathematical Theory of Finite Element Methods, written jointly with his former student, Susanna Brunner. She is now the president of SIAM. The finite element method is the most widely used computational technique for engineering design and analysis. Throughout his career, Dr. Scott developed expertise in fluid mechanics, in large part through his collaboration with the later Bill Parichap. namesake of the WG Parichard Fluid Mechanics Laboratory at Penn State. His talk today is the outgrowth of that work. We are very pleased to have Dr. Scott to present the Marden lecture today. Please join me in welcome Dr. L. Ridgway Scott.
Thank you very much, Dechuan. I remember very fondly, Dechuan was talking about the time in University of Houston where we were pioneers in parallel computing. And I remember very fondly the day Dechuan came to my office. He said, well, maybe I could get involved in this parallel computing. What could we do? And that was the beginning of a long collaboration still going on. We moved into biology areas a few years ago. And so I am very thankful for your introduction and brings back very good memories. And let me say, I'm very honored to be the Marden lecturer this year. And of course, it's a little bit of a new thing for us to be doing these online lectures. So I hope you'll forgive me if I run into any problems. But let me, without further ado, go ahead and share my screen and get started with the talk formally here. Okay, so I trust everybody can see it and see my mouse moving around. So I want to talk about a modern approach to simulating flight. So what I'm saying is there's been a sea change here, a major change in the way we can think about fluid dynamics, especially for modeling aircraft. And let me just say at the outset that this is a collaboration with Ingeborg Gjerde from Simula in Oslo, Norway. And so let me go ahead and jump into this. Why are we interested in this? Well, there's good news and bad news. So the bad news is, of course, the 737 MAX disaster revealed that there is insufficient use of computational simulation of aerodynamics in airplane design. The structural modeling of aircraft is done all the time for aircraft, but the aerodynamics is not used in a substantial way. And I'll talk more about that. And the lecture is really about why not and how things can be changed in the future. On the good side, there are new things happening in aircraft. And here is a nice picture from Joby Aviation of an electric airplane. So for some of you, you may be having trouble getting your arms around the idea of General Motors making electric cars, but people are making electric airplanes. So that's a real challenge because you have to, of course, you got to fly the batteries. But there are advantages to it. And in particular, in this one, you see 6 motors, 6 engines, 6 propellers that are used, and they can be tilted because they're much lighter. Electric motors are much lighter than a regular jet would be. So you can tilt it and you can have vertical takeoff. Some people are designing planes with up to 12 engines. So that gives you a lot of robustness, redundancy, sort of like parallel computing. And it also can possibly be done like a self-driving car. So it's not as hard to fly one of these. So this is a new kind of aircraft that's being designed. And these are in a different part of design space from the existing aircraft that we're used to. And so they offer new challenges and opportunities to look at new designs and new design technologies. And some longtime friends of mine came up with this concept of the new theory of flight that I want to talk about. And that is making critical behavior in flight computable. So let's do a little bit of history here. Let's go back and look at the history of flight. I'm not a historian of science, so I'm going to be doing this with a light touch and with a lot of prejudice, I suppose. But of course, it all started with Leonardo. And he wrote a codex on the flight of birds, and he had designs for aircraft of different sorts. I don't think he really did much implementation, but I think he got a lot of people started thinking about how do birds fly, how could we fly? Some years later, 250 years later, D'Alembert, famous name in science, came up with what he called the potential flow paradox. So he was able to write down an equation, which I'll show you shortly, for fluid flow. But he said there's a paradox that according to this equation, there's no drag. And I'll talk quite a bit about that. Shortly thereafter, Navier and Stokes got involved in modeling fluid flow, and they gave us what are now known as the Navier-Stokes partial differential equations. And I'll show you those equations a little bit later. I'm trying to postpone as much technical stuff as I can for as long as I can. And let me just say at this point, if there are any technical questions that you have, please use the Q&A, and I will address it. If anyone has a question, probably many people have the same question. So don't hesitate to do that, and I'll try to interrupt and maybe go back and cover something that I missed. Okay, so after Navier and Stokes, not that long after, Osborne Reynolds did some famous experiments in which he observed turbulence in detail. Many people have seen those experiments. Basically, what he had was a pipe in his laboratory, and every once in a while, so he's pumping a lot of fluid through the pipe, and every once in a while, a bus would go by outside the building, and he'd see this burst of turbulence. And so he was the first one to observe that. 20 years later, of course, the Wright brothers, without any sort of theory behind it, were able to get a plane to fly. And from then on, we know the story of modern flight. In terms of the mathematical theory, another major waypoint was a paper by Jim Sarin in the late 50s, in which he identified something called that he called the Reynolds-Orr stability or instability theory. It gives you a criterion for whether something is stable or unstable. Now, at the University of Chicago, we always like to refer to famous Chicago professors. Chandrasekhar was certainly one of them, a Nobel laureate. And he wrote a book, a rather thick book, which is back here on my shelf, on linear stability theory. So I'll talk about these two stability theories, the linear stability theory and the Reynolds-Orr stability theory, which is a nonlinear stability theory. And then finally, this new theory of flight. Klaus Johnson and others proposed this new theory of flight, and so that's what I want to talk a little bit about. So back to D'Alembert. What did D'Alembert know? D'Alembert realized that there was something called potential flow. That is, the velocity, flow velocity u, which is a vector function, could be given by the gradient of a scalar function, provided that scalar function was harmonic. So in other words, the Laplacian of phi is 0. The Laplacian is a differential operator with two derivatives in each of the spatial directions. And this is a very well studied type of function, harmonic functions. And so if you have something where you have this harmonic function and you take its gradient, then you'll get the solution of the flow equations that D'Alembert knew, actually the Euler equations. I'll talk about Euler a little bit later. And they satisfy this boundary condition, which says that the normal vector on the boundary, here's a cylinder, and if you take the normal vector to the cylinder, which is just pointing inward or outward, and you dot that with the gradient of phi, that should be 0 on the boundary. That's the normal component of the velocity. So this just says the flow can't go into the cylinder, into whatever the obstacle is. So I'm depicting here a cylinder. It could be a shape, any other shape could be a shape of a wing. This is a two-dimensional flow, and we'll see some three-dimensional flows a little bit later. So this is potential flow. This is what D'Alembert knew. And unfortunately, D'Alembert realized that there was something wrong with that. So we'll take a look at what he knew and didn't know, and see what the resolution of that is, his paradox. So one thing he was missing was boundary conditions. So before Navier, we didn't know how to pose proper boundary conditions. So in addition to the fact that the obvious fact that the fluid can't go through a solid boundary, there's another one which says that the tangential velocity, which is unconstrained in potential flow, undescribed, I should say, Navier said, well, the tangential velocity should be proportional to the shear stress. Now, the shear stress is a force that's generated when you shear a fluid. And so I'll write down what that looks like mathematically, but just think of it as a force. You imagine rubbing your hand along a solid surface, you feel a force, that's the shear stress. And he posed that there should be a proportional constant called beta, the friction coefficient, and I'll introduce the kinematic viscosity, nu. And what's curious, and I'm not so sure who knew this before we started looking at it in the last year, potential flow corresponds to a solution of the Navier-Stokes equations with Navier's boundary conditions for the cylinder in the case when beta is equal to -2 nu. In general, there would be a constraint between beta and nu that would be more complicated, but there's always, to get potential flow, you have to have this negative friction coefficient, which is non-physical, but that's the way it is. It means that the wall would have to be active. It would have to, whenever it felt the shear stress, it would have to push on the fluid rather than retarding the fluid. And many people have thought about ways of having active walls to make flight more efficient. So after Navier, Stokes came quite a bit later, 4 decades later, and really decreed because he was asked to make some sort of make a law about the boundary conditions, and he decreed that tangential flow should be 0, so which would mean beta is equal to infinity. Now there have been lots of tensions between the French and the English over the years, and here's yet another one where the French and the English didn't agree, and I won't say more about that, but we'll talk about it as the lecture progresses. So here's back to potential flow and what D'Alembert knew. D'Alembert knew that there was this potential, in fact, for the cylinder. It's a simple algebraic function, so D'Alembert knew this. D'Alembert could compute the drag based on this, essentially because of the symmetry of the flow. Not only is there up-down symmetry, but there's a type of fore and aft symmetry to the flow. And D'Alembert realized, based on that and some other things that he could compute, that the drag would be 0. Now, if we go over here and take Navier's boundary condition, here I've taken beta equal to +2. And what you see is, well, the flow definitely changes. It shifts a little bit more to the right, more downstream. It's coming from the left, going to the right. And so the Navier slip condition definitely gives you a different kind of flow pattern. And we'll see, in fact, it gives you a definite drag. So that resolves D'Alembert's paradox. Okay, so here's D'Alembert's paradox. D'Alembert knew this was wrong. Just common experience indicated that there would have to be drag, and so he was just confused. So we can see now today that, because we are able to do these computations, which D'Alembert couldn't have done, that there really isn't a big paradox. It's this flow on the right definitely has drag, and so that paradox goes away. Okay, well, now what about this new theory of flight? Well, in this paper published in 2016, Klaus Johnson and 2 former students, Johan and Johan, Hoffman and Janssen, said essentially this, that flight can be explained by potential flow augmented with rotational vortices. Okay, so I'll show you what those look like. Let me just say potential flow, it could have been interpreted as laminar flow of the type I just showed you. That's not really what's essential. It's a laminar flow with rotational vortices generated, interestingly, at the trailing edge of the wing, and the instabilities are just caused by small perturbations of the flow. So we're going to modify and perhaps clarify this a little bit to suggest that we use Navier friction boundary conditions with beta positive, not exactly. Potential flow would be negative. And for instabilities, we're going to pick the Reynolds or kinetic instabilities. So here's what, this is a figure from that paper by Klaus Johnson and the Johans. And the flow is coming from the left here and hitting the cylinder, and then goes over the back of the cylinder. And strangely, these vortices start rolling up off the back edge of the cylinder. Well, first of all, why do these vortices form? Why don't you get that laminar flow pattern I showed earlier? If there's going to be instabilities, why do they come off the back edge of the cylinder? Why don't they start at the beginning? I would have thought naively, if they're going to be instabilities, they would be generated at the leading edge, where it first hits, runs into the air. Now, strangely, they're at the back end. According to their computations, they're at the back end. So that's one thing I want to try to explain. Why would there be instabilities primarily at the back end of the cylinder or an airplane wing and so forth? Okay, so as I say, the main feature of the new theory is that the instabilities occur at the trailing edge. And they had arguments. Johnson and collaborators had arguments as to why this would occur, but not any sort of really well understood instability according to any mathematical theory. However, the Reynolds or kinetic energy that was featured in Saren's work does give a precise mathematical condition and prediction of these instabilities. So that's what I want to focus on a little bit, to tell you what that Reynolds or theory looks like. And I want to say a little bit about conventional stability theory and why that fails. So I have to say a little bit about what it is, but I'm not going to dwell much on that theory. The pedagogical theory that I like says that if you want to teach something to students, you tell them the right way to do it first, and then you can tell them the wrong way. But if you do it the other way around, they'll always remember the wrong way and do that first. So I'm going to tell you the right way, which is Reynolds or, and then we'll come back and say a little bit about the other. So both of these involve solving an eigenvalue problem, but the linear stability theory predicts instability at a given Reynolds number, well, when it works. Whereas the Reynolds or kinetic energy instability theory, which I will often just say the energy instability theory, it predicts instability above a certain Reynolds number. So it says, here's a mode that will go unstable at Reynolds number X, whatever that number is. Reynolds number means how fast is the flow going. So the faster the flow, the bigger the Reynolds number. Same Reynolds that did the turbulence experiments. So not only does it say that this mode will remain unstable, but as the Reynolds number gets bigger and bigger, there may be more and more unstable modes. So ultimately, there can be a large space of instabilities. And I'll show you a picture of some of them, but it can get very large for large Reynolds numbers. So why would this have been missed? After all, Reynolds and Orr were in a previous century, maybe a century and a half ago. Well, one answer might be that the linear stability theory actually asks you to solve an equation, and then that gives you an equation for the unstable mode. Here, it's a little bit more complicated. We're going to solve an eigenvalue problem, and that'll give us a mode, and that mode will be unstable for all Reynolds numbers above a certain size. So inequalities are a little bit harder to understand than equalities. I certainly had that experience when I was younger. I was always used to solving an equation. And then somebody said, well, you just need to prove an inequality. And I said, really? What's that? So took a while to get used to that. And so this is like that. This is an inequality that governs the instability. Okay, so finally, here are the differential equations called the Navier-Stokes equations. So they're an equation for the fluid velocity, U, and the corresponding pressure, P, that describe the fluid flow. I'm talking about incompressible fluid, so their divergence of U has to be 0. Most fluids in the world are incompressible. At very high speeds, air can become compressible, or if you are pumping air into your bicycle tire, you are compressing the air, but just the air in the room is incompressible. And certainly for airplane flight under about 200 miles an hour, everybody agrees that incompressible is the right equation to use. But now let's talk about how the flow evolves. So the time derivative of the fluid velocity is given by a term which involves the kinetic viscosity, nu. So that's a viscous term that sort of slows things down. This is a directional derivative. This is saying that the change of U will occur in the direction of the flow. So the change of U in time is proportional to the change of U in space along the streamlines of the flow. And then those three terms add up to 0 modulo the gradient of a pressure. And this additive term allows you to ensure that the divergence can be 0, but of course the pressure is a critical thing. We typically don't think about the pressure. The pressure on the surface of the Earth is about 15 pounds per square inch. It's pretty constant. So the gradient of the pressure is typically 0 and it doesn't enter the equation, but nevertheless it's there. Now we want to talk about instabilities. So what do I mean by an instability? Suppose there's another solution. So we've got this one solution U and we have another solution W. And so we assume that W satisfies the same equation as the same Navier-Stokes equations as U does, but it differs at time equal to 0. So U at time equal to 0 is equal to W plus a small perturbation. So the difference in U and W is a small perturbation V. Okay, now what we're interested in is when does this perturbation give rise to an exponentially changing solution? Now, in other words, we're thinking of instabilities where the solutions diverge exponentially fast. So that's a strong condition, but nevertheless, one can go through some math. And by the way, this is an advertisement for my talk tomorrow at the colloquium. I will go through all this math and show you how it works. But the bottom line is fairly simple. It's an inequality. I said it would be an inequality. It says that if you take the initial condition, so I take U naught is where U is at time equal to 0, and we're trying to decide is the flow unstable at this point. If you take that U naught and you take its gradients, that's its first partial derivative. So the gradient of a vector valued function is a matrix. So I take the matrix grad U naught and its transpose and add them together. Now I've got a symmetric matrix here. And I take the dot product or the vector product with the proposed perturbation V. So V is this perturbation. I take the integral of that over the whole space where the fluid is held. If that expression is bigger than nu times this positive quantity. So this is not the kinetic energy, but I'm forgetting the name of the energy, but it's the derivative energy of the flow. So that's a positive quantity. And then here is a boundary term that involves the Navier boundary condition. So this is the projection onto the tangent space of the obstacle. So if the tangential velocity of the square integral of that, square integral here, so it's a positive quantity. If that's less than this expression on the left, then you have an instability. Okay, so that's a lot to digest, a big mathematical expression, but we'll just use that. That's the Reynolds or stability test. And again, I will go through that in detail tomorrow. Okay, now how do you determine if such a condition holds? Well, one way is to divide one by the other. And then, so I do that, I divide by this positive expression. And so what I'm looking for is how small can that expression get? Well, I could take lambda be the minimum of that. So instability occurs if this parameter lambda is less than -1. The corresponding minimum function v, which can be identified as an eigenvector of a differential equation, is the corresponding unstable mode. Okay. So, so this expression is what is dealing with. So it can be of any sign because this matrix has eigenvalues given by the eigenvalues of that sum, the trace of the eigenvalues, the sum of the eigenvalues, the trace of that matrix is equal to the divergence. And since we've got something that's divergent 0, then this matrix can have both positive and negative eigenvalues. And so, although sometimes this might be positive, sometimes it can be negative. And so whenever that happens, we have an instability. And if there's more than one eigenvalue for the corresponding eigenproblem, then you'd have more than one unstable mode. Okay, so I've introduced Reynolds or stability condition. And your first question should be, well, can you show me somewhere where it works? Where does it matter? Well, let's do Couette flow. Couette flow is the simplest flow pattern to think of. It's a simple linear flow. So here's the formula for it here. We've got the velocity is equal just to constant, the speed, divided by this height parameter, times a vector. It's a two-dimensional flow. It's 3-dimensional, but I've written it here just in 2 dimensions. It's constant in the 3rd dimension. It's given by the height here. You can see this laminar profile. It's the height y, and it's 0 in the vertical direction. So the flow is just going just through here. And so it's moving to the right at the top and to the left at the bottom. That's the simplest flow I can imagine trying to explain to the student. So exercise, you go say, well, does it satisfy the Navier-Stokes equations? Yes. Essentially, all the derivatives vanished. The pressure is constant. The complicated one, of course, is the u dot grad u term. But if you haven't done calculus for a while, maybe you'll enjoy going through that exercise to see that that's 0. Now, what's interesting about the Couette flow profile is that it's valid. This simple linear profile is valid for all speeds. So no matter how fast you push it, no matter how fast you push those plates, you still get this linear profile. Okay, so that makes it very easy to study at any speed we want. What's strange is that according to the linear stability theory, this is linearly stable for all flow speeds. And it's not just an opinion, it's actually a mathematical theorem that's been proved in the recent decades. So that's the way it is. So we have a flow which is according to linear stability theory, stable at all speeds. But everybody knows it's unstable. Well, there have been experiments, physical experiments done with, moving plates to look at that flow, and computational experiments, which suggested instabilities at about the same Reynolds number. And so we did the computations for the Reynolds or instability theory. And lo and behold, here's what we got. The flow profile in green is the most unstable mode that satisfies that minimization problem, which is the same as an eigenvalue problem. And so the theory says that will be, it's a theorem, that will be exponentially unstable. And so we also did that calculation. So we solved the Navier-Stokes equations, integrating in time with the shear profile of Couette flow plus this profile in green. Now, let me just say, maybe at a simple level, you can say, well, yeah, that makes sense, because the flow is going one way and this unstable mode is kind of going against it. So that's sort of what you'd expect. It's something that's interrupting the flow. Now, what I've plotted here is the horizontal component. It's just easier to see. So this is the flow. Remember, the flow is only is moving in these two horizontal directions, and so this is the perturbation that causes it to change. And so what we did was we said, well, how big does it get? And we measured it in the integral of the gradient squared of the velocity, that term which is in the Reynolds-Orr criterion. And what you find is that, yes, indeed, it grows, at least for the Reynolds number, significantly large. I picked 1600 because that's the number at which the experiments had showed that Couette flow was unstable, and also comparable numerical experiments had done just by integrating the equations and introducing some small perturbations. So we sort of knew that that should be unstable. Now, we actually showed that it's unstable, not so dramatically, but it's unstable for Reynolds numbers above about 177, 176 and change. So our calculations showed that it's unstable for an even smaller Reynolds number. And I'll give details on that tomorrow in the lecture to the math department. You'll see rigorously where it's stable just below that and unstable just above that. But here we're seeing some rather larger Reynolds numbers, faster speeds. And what happens is that the perturbation grows, really, it starts out exponentially and then really goes super exponential for a while. It does saturate at a point and then it decays. Now it's interesting, it's not decaying monotonically, it's sort of wandering around a little bit. We were able to do even larger Reynolds numbers, and you see even larger perturbation growth and a longer time for it to get back down to the, so you see that this was out to time 5, and for Reynolds number 10,000, it's just about gotten back to where it was. If you go to Reynolds number 30,000, it takes longer, and 100,000 even longer. This is out to Reynolds number 10. And here in the table, I've gathered all that together. So I call TP the persistence time. How long does it take for the flow to go up and come back down to where it was in size? That's TP. And that's where we see the most happening here. So the persistence time grows the most with Reynolds number. I mean, it's not proportional to Reynolds number. Maybe it's logarithmic in Reynolds number. I don't know. I don't have a theory to explain that. The amplitude grows. It doesn't grow quite as much as the persistence time does. And also the time at which the maximum occurs grows as well, but even less fast. So that's a snapshot of the way the unstable mode, most unstable mode for Couette flow grows. And it's consistent with what we would call a turbulent burst. So in other words, you have a small perturbation, that perturbation grows, and then eventually it decays. Exactly what Reynolds observed in his first experiments. Okay, so why was this missed? Why has it taken this long to see this instability for Couette flow? Well, I don't really know. I've thought about it a lot. Possible reasons might be the inertia of linearized stability analysis, which has been around for 100 years, despite the fact that Reynolds and Orr suggested something different. There, I can't quite explain it. I think that's a question for mathematical historians to look at, science historians. One thing I will say something about is there are old and new ways about thinking about partial differential equations. And you might have said, well, Sarin is the one that realized Reynolds-Orr theory was the right one to use, but he was focused on stability, proving stability, which he did, and not instability. And besides, even if he had, he wouldn't have had the computing power to be able to display the pictures I just showed you. But the takeaway message I want you to think about is that kinetic energy stability theory or instability theory is natural in what's called the variational approach to PDEs. That's the modern approach to PDEs. And I want to say a little bit about that now. So we saw a history of the history of flight before and theory of flight. Here's just a short history about partial differential equations. Well, it all started with Newton, of course, and Leibniz, the notion of derivatives. Euler, by Euler's time, he was writing down what are called the Euler equations. So that's the Navier-Stokes equations without the dissipative term, without the viscous term before Navier and Stokes. And let me just give you a little context here to think about how things have changed. So in Newton's time, negative numbers were considered absurd. Euler was the first one really to establish complex numbers. So these are early days. So the fact that Euler didn't quite see all of this in his time is not surprising. D'Alembert came slightly after Euler. He saw that the potential flow gave a solution to the Euler equations, but he realized there was a paradox. Well, after Euler, there developed a bifurcation between mathematicians and, let's say, practitioners, people like Chandrasekhar. Dirichlet was the first one to realize this variational principle. It was later developed more fully in what we call functional analysis by Banach and Hilbert. The concept of duality is critical to the understanding of certain partial differential equations. And then I'll say that the variational approach got fully developed by Jacques-Louis Lyons, Sarin, and many other people. And that's now the modern approach. So modern mathematicians and many engineers today would use this variational approach, whereas this older approach persists also in engineering and in parts of science. So this bifurcation is part of the reason that this Reynolds-Orr theory was not used. Okay, so the linear stability analysis just doesn't work. It's necessarily approximate. It approximates the Navier-Stokes equations by a linear approximation. It gives you a linearized eigenproblem, but it's not a symmetric problem. The one for Reynolds-Orr is symmetric. When you get a solution, you have to make an assumption that there is a nearby solution to the Navier-Stokes equations. To prove that would require some sort of stability property, but you can't use stability to prove instability. So the reasoning is just broken here. So we're going to say, don't do linear stability theory anymore. Okay, so back to the big question. Why does this matter? Well, I claim computational simulation of aerodynamics is not in the critical path of airplane design today. I have to be careful about that. Let me say what I mean by not in the critical path. People at airplane companies would say, oh, no, we do a lot of simulation and we pay a lot of attention to it. But what I mean by that is that, in particular, stall prediction is beyond the capability of most codes. And when they had trouble with the 737 MAX, they didn't go back to the computer laboratory and do simulations to see what happened with regard to stall. They just simply boosted up this MCAS system. And then I guess everybody else knows the rest of the story. It's very unfortunate. But we claim the new theory of flight has the prospect of explaining critical behavior, maybe not every detail, but predicting when stall occurs, predicting the lift and the drag, which is critical to determining the efficiency of aircraft. And so we are proposing that as the way forward. Okay, so let me just remind you what that theory is telling us. It's telling us that we have flow coming into an obstacle. It doesn't go unstable at the front of the obstacle. It goes unstable at the back of the obstacle. So can our new instability theory predict that? We've seen that it predicted couette, flow, instability, but now here's a more challenging one, flow past the cylinder. Okay, so we haven't even submitted this yet, so this is fairly new computations, but here's flow past the cylinder, the two-dimensional case to begin with, and here's what it looks like. So there's this instability, the flow is coming from the left, and this instability occurs at the back of the cylinder, just like Johnson and collaborators said. So, whoops, sorry. There we go. Let me show you what the most unstable three-dimensional flow looks like. It looks like this. So what you see is that the flow is going one direction here and another direction here. That's exactly what the Johnson and collaborators found for the instability, again, at the back of the cylinder. Now, curiously, it turns out that the most unstable mode in 3 dimensions is the 2-dimensional mode. That was surprising to me, but in any case, that's that we find the next most unstable mode is a 3-dimensional mode, and it's consistent with what was found before. There are many instabilities, lots of pretty pictures. Here's one of my favorite that occurs at a different eigenvalue, so less unstable, but at a high enough Reynolds number, this sort of instability would play a role. Okay, so let me shift now. We're running out of time. Let me shift to the drag question that D'Alembert raised. So I want to remember I've got the viscosity parameters and the friction parameter. So this is the physical viscosity. This is the Navier friction parameter. And we're computing the drag coefficient. So drag is proportional to the speed squared divided by the density of the fluid times a constant. Well, it might not be a constant, but remarkably, this constant has been measured experimentally, computationally. A lot is known about it for all kinds of different obstacles. And it is largely constant for most speeds. And the constant happens to be 1. And that's what we get. We get 1 with sufficiently high Reynolds number. So this would be a Reynolds number of about 200. And for enough of a friction parameter to be significant. Now, if you take the friction parameter to be 0, well, we don't get quite the right prediction of drag. And of course, if you take beta equal to -2, you have potential flow, and you get, as D'Alembert noted, you get 0. But you do get the right answer with just a little bit of friction parameter, and that's really quite striking. It's surprising that it doesn't take a very big friction to give you the right drag. So what we're saying here is the picture is pretty simple, that you can take laminar flow with an understanding of the unstable modes and predict what you would see for flow past an airplane and other obstacles. And you get the drag computed fairly easily. So it's maybe not as complicated as we've been thinking. This may even give us a new approach to turbulence. I worked on turbulence early in my career. These 3 papers are part of that. As someone who worked on turbulence for almost 50 years, I think I'm allowed to say this approach, the stochastic approach to turbulence, has not been a complete success. So in fact, turbulence may be multifaceted. We now understand cancer as being very multifaceted, and I suspect turbulence is multifaceted. So we have to think about looking for different kinds of explanations for turbulence. So turbulent bursts are one thing that are very well understood experimentally, and now maybe theoretically, because our computation with Couette flow exhibits such instabilities that lead to turbulent bursts. And there may be even persistent instabilities. There's some people that propose that there could be persistent instabilities that could be interpreted as turbulence. Okay, so now conclusions and implications. So conclusion, the new theory of flight holds promise to change qualitatively fluid flow simulation, put it in the critical path of design of aircraft. We can use computational simulation to optimize designs and assess deficiencies. We think we can talk about, we think that the techniques that we haven't, I haven't talked about the techniques that Klaus Johnson and others developed. Those, I believe, can predict the thing that caused the max problems, the stall of an aircraft. And I should say, my colleague Johan Janssen is currently involved in a stall prediction workshop that NASA is hosting. So we should be able to improve performance of all kinds of vehicles, propulsion systems, all kinds of engines, energy generation, wind generation, for example, medical treatment of problems in all parts of the human body. And maybe there's a new way to think about turbulence. We could potentially have more realistic flight simulators for pilot training, and ultimately perhaps computational certification of aircraft. With all these new electric aircraft coming online, one problem with that is the cost of certification. So if we could do some computational certification, that would be a big advance. Okay, well, I've talked long enough. Let me just thank again Ingeborg Gjerde, who's my main collaborator on this, as well as several other people who were very helpful along the way for their valuable suggestions. And let me just say that my understanding of this subject was enhanced substantially by a particular book by Johan Hoffman and Klaus Johnson. And with that, I will show you some references. Number 4 is that book that I was just describing. And with that, let me open up the floor to questions. Thank you very much for listening. And okay, Sarah Patch asks a very interesting question. Thank you, Sarah. And I did not, you can email Sarah to verify, I did not pay her anything to ask this question. What types of medical treatments involve turbulence? Well, good question. Certainly flow in the heart. So turbulence has to do with the Reynolds number. If the Reynolds number is low enough, you don't get turbulent flow. Flow in the heart is certainly turbulent. I've recently been working with some people who work on the intestinal system, and there the Reynolds number is just over the edge, so you can get turbulent flow. So those are two different regimes which are quite different. I will say the flow in the intestines are not Newtonian flows. Those are non-Newtonian flows. That's another talk I'd be happy to give. I've been talking about water and air, which are Newtonian fluids, but non-Newtonian fluids describe most bodily fluids. And so that's a very interesting question to look at that. So what we're hoping to maybe look at that in the near future. So we'll try to get back to Sarah with more details on that. Okay. And Fred Melender says, you mentioned that air can be considered incompressible for speeds under 200 miles an hour. How does the theory change for aircraft flying above that speed? That is a very good question. And I have to be a little bit cautious here. We have been looking at incompressible flows. And so it requires a different changes to that approach to do compressible flow. In full disclosure, I should say that the results I was showing for the Couette flow was using this so-called Stokes boundary conditions, the no-slip boundary condition, whereas in doing the flow around the cylinder to match the experiments done by Johnson and colleagues, we had to do the slip boundary conditions, and that required changing the theory, not a big way, but so going to compressible flows will require a little bit more sharpening of the pencil and working out some equations. So again, email me and I'll keep you posted.
Any other questions?
Two great questions, I will say. I didn't pay either one of them to bring those up. Those are really critical questions, which are ones we'll be looking at in the future.
Well, if that is not the case, then let's thank our speaker again. So I'm gonna clap for the audience.
Thank you very much.
And yeah, hopefully next spring in person again. And until then, everybody stay safe and healthy.
Well, thank you very much. Again, this was an honor, a great honor, and I really enjoyed it. And thank you all for listening. And okay. So there's one more quick question. Can we just do that?
Yes, yeah, absolutely.
Okay. So the Reto Frey, I'm sorry if I get your name wrong, said, how does this relate to the Prandtl theory? Well, it's quite different. So the Prandtl theory is an approximate theory. And I advocate with Navier-Stokes, it's so unstable. I haven't emphasized how unstable it is, but if I could show you more pictures, you'd see what I'm talking about for flow past the cylinder. As the Reynolds number grows, there are just more and more instabilities. You can't make approximations. You have to have something, you have to stick with exact solutions and exact perturbations that are known to be unstable, rigorously unstable. So the Prandtl theory just has to be redone. I'm sorry. It was, again, on that path of using PDEs naively, not the modern approach to PDEs. So it just has to be looked at completely from scratch at this point. Oh, okay. So another person here, another Scott, Ron Scott, my brother, was listening. He says, is air at sea level not compressed more than at altitude? Yes. Okay. So this is a very important point that makes it a little bit complicated when you talk about airplanes. So once you get up at the altitude, the density has changed. And so there's a way you have to take into account what altitude you're talking about. So to be a little bit more precise, we're talking, say, at a plane flying at about the speed they do when they're landing and near the ground. So they're, you know, if we're really doing the real calculations, we would have to account for flying at altitude. So there are some details here I've not fully disclosed. Yeah, it takes time to think of the questions and then to type the questions into Q&A. You know, maybe what we need to do to build into these lectures a little advertisement and generate some cash for the institution that's putting it on.
That's a great idea.
I'm sure the University of Wisconsin-Milwaukee would be happy to have donations. So if anybody of you feel motivated, do consider it.
Okay.
Excellent talk. Thank you.
Everybody for being here.
Well, thanks again. I enjoyed it very much. And again, thanks for the honor.
Excellent talk.
Thank you.